encryption method based on one-dimensional random scrambling.
Welcome to one and all present here. I am Madhu Rohini, Sri Balaji and Sri Bhavana. We are undergraduate students doing our final year BTech in Computer Science Department, Keshav Memorial Institute of Technology. Our topic for today is an improved and scalable digital image encryption method based on one-dimensional random scrambling. This is done under the guidance of Dr. Ravi Shankar, HOD of Computer Science Department, Keshav Memorial Institute of Technology. The flow of our presentation can be discussed under the following headings: Introduction, Quidamson's algorithm with its description and drawbacks, our proposed method which can be divided into block shuffling and interblock pixel scrambling, its advantages and conclusion, and its finally the future scope. Now, with the advances in multimedia technology, security for information has become very highly essential. Encryption techniques are being used for the same. Now, encryption techniques for textual data and for images, they are totally different. But today, our interest lies in image encryption techniques, and some of which are watermarking, which prevents copyright infringement, and scrambling, wherein we encode the message or image in order to prevent it from being accessed in the original form, and hiding, wherein we hide the text within the image, which is called steganography. But we found scrambling to be the most effective out of all these three techniques. Quidamson's algorithm is the base paper on which our method is actually based on, and this particular algorithm has the following steps. First of all, we take an image of n cross n dimensions, and then we transform it into a one-dimensional vector which is of type n cross n again. Now we generate two distinct random sequences. Drawbacks of Quidamson's algorithm now are scalability of the algorithm, which is due to the size of the image. That is, as the size of the image grows, the size of the one-dimensional vector also grows. So this affects the scalability of the image, as because the size of the image that keeps growing, it becomes difficult to generate that vector. And also the algorithm as such is sluggish in its execution, because the time taken is very large, because the random sequences themselves are of the image size. So as the size of the image goes on increasing, it becomes inefficient and impractical to generate such a large sequence. This presentation will be continued by Balaji, who will discuss and give you an insight on our proposed method.
Hello. Now, as you can see, there are a lot of drawbacks in this Quidamson CT algorithm. So we have devised an improvised algorithm which can overcome all these drawbacks. So in the first step, let me describe how this algorithm works. It has three simple steps. We try not to complicate it. First, we will take a two-dimensional image, divide it into a convenient number of blocks. Now, once we have these blocks, we will shuffle this using a random sequence. So thereby, we are creating a jigsaw image. Now, after constructing this jigsaw image, we will take that as an input for our step 3, and we will scramble the pixels across the blocks. So the first operation is block shuffling. So in this first, let us understand this simple with a scenario. Let us take a two-dimensional image of 96 cross 96 image. So, and let the block size be 32. So overall we will be getting 9 blocks, and we will be generating a random sequence of length 9 from 0 to 8. This will be we have to generate cryptographically very secure random sequence. And using this particular sequence, we will be constructing a jigsaw image. I'll present you a small animation of this. Let's say this is our cameraman image. First, we have divided into blocks, and using that particular sequence of length 9, we are constructing a jigsaw image. So as you can see, let's say the first position was 0, it got interchanged with 0. Now after getting all these pixels, we'll construct the jigsaw image, and this after constructing this jigsaw image, it will be given as an input to our step 3, that is performing the interblock scrambling, or simply can be understood as scrambling across the blocks. So now we have all these blocks. So in the interblock pixel scrambling, first we need to generate a random sequence of k square. Continuing with our previous example, we took a block size of 32 cross 32. So essentially we will be generating two random sequences. Let's say for simplicity R1 and R2. R1 and R2 will be of length 1024. And using these two sequences, we will be performing the interblock scrambling. A small animation is shown. Let's say this is now our jigsaw image. This will be input to our step 3. Let us take the first number in our R1 sequence is 38. and the second number in our R2 sequence is 128. So we will be locating those pixel positions in not only in the first block but across all the blocks. And now we will be doing the pixel scrambling using the jigsaw sequence. So this is how the pixel scrambling occurs. So this is carried out for all the blocks and for the 38 and 128 pixel position. These two are only the first two numbers. Similarly, process carries out for all the numbers present in R1 and R2. So after this particular pixel scrambling is done, we will get a scrambled image. Now we have presented a comparison between how encryption occurs from Quidam cells and proposed algorithm. As you can clearly see, we are achieving the same amount of scrambling degree even our proposed algorithm and overcoming all the difficulties. So this presents our comparison. Finally, I would like to conclude that here we are, as you can see on the table, we have presented a comparison of memory consumption and execution time. So clearly we have overcome all the demerits. And in Quidam cell, let's say we have a huge image of 1024 cross 1024. It's a poster kind of image. So we will have to generate the vector of 1024 square. But in this our proposed algorithm, we just have to generate a random sequence of 32 cross 32, which is our block size. So essentially, we have scaled our algorithm for large size images, and also we have achieved similar encryption quality. So this is our conclusion. So hence, I propose that our algorithm is better than the Quidam Sun's algorithm. Thank you, Bhavana.